Isaac Newton proved two theorems for spherically symmetric systems that greatly simplify obtaining their potential. Newton's first theorem states that a body that is inside a spherical shell of matter experiences no net gravitational force from that shell. Let's see how we prove that. Let's consider the shell in here. If you consider the cones here, if you define this point R, and then you have these two cones, this one that is radiating from R, defining the cone of solid angle d omega, and the other one on the opposite direction, this cone, it intersects the shell at two locations, one of angular extent theta 1, and the other one of angular state theta 2. Now, the mathematical expressions of theta in terms of the solid angle are, so the masses then dm1 and dm2 that are contained in these arcs, they are in the ratio that dm1 over dm2 is equal to r1 over r2 squared, because the mass is proportional to the length of the arc since the density is constant. The acceleration that a test particle is feeling at point r by the mass here that is contained in the arc theta 2 is dm2 over r2 squared, and the acceleration that is felt from the mass that is given by the arc theta 1 is equal to dm1 over r1 squared. The acceleration is equal and opposite, and therefore, if you integrate over all the directions, the sum is 0, proving that there is no net force experienced inside the spherical symmetric shell. Now, as a consequence of the theorem, if the acceleration g, which is minus the gradient of the potential, is 0, that means that the potential is constant. So we can take the potential at any point inside the shell, and it will give the potential anywhere. For convenience, then, we choose the center of the sphere. At the center of the sphere, any mass distribution is at a distance r, so we can easily calculate the potential. So that's the potential inside the shell.